Thank you very much. I'm extremely glad to be here. I'm Deborah Mayo, and as Dan said, I'm a philosopher of science and of statistics, and I'm very grateful to the organizers of this session on significance test controversies and to my co-panelists for many months of presentation. So, how should we rethink the controversies of statistical significance? They're very old and also very new. And it seems to me that we learn a lot by looking at today's replication crisis, these high-profile failures of replication, even though they're so much the source of criticisms. A failed replication occurs when a result that had been found statistically significant is not found significant by an independent group that tries to replicate it only using new subjects and with much tighter experimental controls and with pre-designated hypotheses so that you can't so readily go on the kind of fishing expedition that this character is undergoing in the cartoon. So the replicationist relies on significance tests to determine if there has even been replication, and whether or not your field is in crisis depends on the results. Some people object to the very idea of subjecting researchers to replication, calling the replicationists terrorists and bullies and tearing down fields that others have built up. And some, like Daniel Kahneman, issuing rules of etiquette for running replications, such as including the authors in the planning of it, lest they go ahead and sabotage the results altogether, as many will be tempted to do, Kahneman says. So I'm going to address our question directly by considering how an enlightened significance tester, the sort that would be trusted to do replications, might respond to challenges in light of today's replication skepticisms. We don't assume that there is a single method or a single school that's going to be adequate for all the complex tasks of statistics, but still, in using a significance test, the tester might need to respond to skeptical replies or skeptical questions about why use this tool rather than some other for the particular problem at hand. So I will begin with criticism raised by John Ioannidis in his infamous 2005 paper, where he says that several methodologists have pointed out that the high rate of non-replication is a consequence of the convenient but ill-founded strategy of claiming conclusive research findings solely on the basis of a single study with a small p-value. So to distill this as a question, it would be, why would you use a tool that infers from a single small p-value regarding a statistical hypothesis to a research claim, let alone calling it conclusive? The simple answer that the enlightened significance tester would give is, well, we don't. We know from the founder, R.A. Fisher, of significance tests, who always said, we're not interested in isolated records, but with reliable methods of procedures. And you can't say that a phenomena is experimentally demonstrated unless you know how to conduct an experiment that rarely fails to give you statistically significant results. So the thinking is, if the null hypothesis H0 is an adequate description of the data generation, then with very high probability, you wouldn't be able to regularly produce statistically significant results. So if you do, it's evident that the null hypothesis H0 is false in at least the manner probed. This is the pattern of falsification in science in general, which is nearly always statistical. However, even if you have evidence for some real effect, it's not going to be evidence for some substantive research claim, call it H star, because nearly always H star is going to make claims that have not been probed by the statistical test. We all know statistical significance isn't substantive, correlation isn't cause, and so on. I think it's true, though, that the moves from experimental interventions to substantive research claims hasn't really got enough attention in today's replication crisis. And these often go beyond statistics to theories about measurement and substantive theories, but at least your statistical account should block that immediate move that Ioannidis claims they all do. Neyman-Pearson tests are very explicit about restricting the alternative hypothesis such that the inference is always just to an alternative statistical claim, not a substantive research claim. But then you might get the question, why use an incompatible hybrid of Fisher and Neyman-Pearson? The truth is that they're not incompatible. They mathematically dovetail. They both fall under the umbrella of tools for, as Alan Birnbaum says, appraising and bounding the probabilities of seriously misleading interpretations of data. These are error probabilities, and so we can call the account error statistical, and they include confidence intervals and tests, but also resampling, randomization, and much else. And all of these founders showed that error control is invalidated by selective reporting. Fisher called it the political principle. Also by multiple testing, by what we now call p-hacking. I'll call these all biasing selection effects. I really think we need to get beyond this inconsistent hybrid idea, even though there's a grain of truth to the supposition that Fisher stressed inferential interpretations of p-values and Neyman-Pearson tended to stretch more long-run performance. But the inconsistent hybrid leaves us with caricatures where Fisherians are not allowed to use power and anybody using a Neyman-Pearson test is not allowed to use p-values. In fact, the very founder, an associated person, student of Fisher, and key spokesperson, Eric Lehman, made it clear that we really want to hear the p-value. We want to know at what would be the smallest level that this result that would lead to rejection. And moreover, he says that the p-value gives us an idea of how strongly the data contradict the hypothesis and enables others to reach a verdict based on their own significance level. So there never was this idea that Neyman-Pearsonites can't use p-values. I say drop all the personality labels, the Fisher, Neyman, Pearson, and also drop that acronym NHST null hypothesis significance testing, which is too often associated with the abusive cookbook statistics that have long been deplored. The term statistical tests or error statistical tests will do. Next question, why apply a method that uses error probabilities to begin with? The sampling plan comes in different forms. Research intentions about when to stop. You should condition on the particular data. Response of our enlightened significance tester. Well, if I did condition, I wouldn't be able to use error probabilities, and I need them to assess how well or poorly tested claims are. Think about this. What bothers you when cherry pickers selectively report? It's not a matter of long runs, even though that would have a very unreliable long run result. But that's not the thing that bothers you. What bothers you is, in the case at hand, you can't say it's done a good job of avoiding sources of misinterpreting data. And your account ought to have a principle that makes sense of this intuition. Namely, you haven't been given good evidence of a genuine effect if a method makes it very easy to find some impressive-looking effect, even if it's spurious. And this general principle goes beyond formal testing. I think that it implies for any claim, including estimation and prediction and a model test. The point is that it isn't enough that your data fit the hypothesis. It has to be that the account has probed the ways that it can be false. Otherwise, it's passed a test, but it's not very stringent or severe. So, in responding, you can agree with those who point out that p-values can only be used once the sampling plan is known, and in fact, Bayes factors can be used in the complete absence of a sampling plan, and simply say, we must be in very different contexts. I'm in one of those skeptical contexts that led fraudbusters to advise what they call the 21-word solution. This is Simmons, Nelson, and Simonson, where they say the researcher must disclose all aspects of the sampling plan in the methods section in order for the result to be taken seriously. Have you given yourself several extra chances in the forking path from data to inference, as Gelman and Loken call it? Inquiring minds want to know. Yet, some accounts of evidence, and this is Stephen Goodman, object to the way frequentist inference deals with multiple comparisons and multiple looks, namely by adjusting the p-value. He says adjusting the measure of evidence because of considerations that have nothing to do with the data defies common sense. And Steve Goodman, by the way, is the co-director with Ioannidis of Meta Research Center at Stanford. So his inference account tells him that, but to a skeptical tester, these have a lot to do with the evidence, and the adjustments are important. There seems to be a tension with this attitude and with pre-registered reports, which are supposed to be the way to restore replication. Isn't it that your appraisal would be altered if you consider the researcher flexibility? Once you compute what's the probability that some hypothesis, some stopping point, some subset or other would have led to a false positive. And what you're doing there is looking at the sampling distribution. It's true that there are many ways to correct p-values, and some people really object to them. But they're appropriate for different contexts, and some fields like high-energy particle physics will report several of them. The main thing is to have an alert that in the face of biasing selection effects, your reported p-value is invalid or questionable. Here's the third response to the same question: why do you use error probability? Answer: I don't want to relinquish my strongest criticism of findings that are the result of biasing selection effects. What happens is, wanting to promote an account that downplays error probabilities, critics find themselves turning to other means, notably giving a high prior probability to the null hypothesis of no effect, using a Bayesian analysis, so a low probability to the reality of the effect. That might work in some cases, but there are problems. For one thing, the researcher deserving criticism can deflect this by saying, you can always do that. You can always discount my effect by giving a high prior to the no effect null. Moreover, it really gets the blame in the wrong place. These data-dependent hypotheses, post-data subgroups, are often very plausible. That's what makes them so seductive. And even if you do want to say they're plausible, you should go on and say, but this is a poor test of it because of the searching. Next question, why use methods that exaggerate the evidence against a null hypothesis? We hear this a lot. Again, it's old but very new in the move to reinterpret significance level. I will just quote this group paper here that explain whether p-values exaggerate depends on one's philosophy of statistics. P-values might appear to overstate evidence based on comparing p-values to quantities like likelihood ratios and Bayes factors, and those measures are important in Bayesian analysis, but many other statisticians do not accept these quantities as gold standards. And it's very remarkable that this group agreed to put out this statement. This whole p-values exaggerate idea comes from the conception of testing a point null hypothesis, giving a lump of prior to the point null, and then appropriately spreading the rest of the prior to the alternative, and this famous result, the Bayes-Fisher disagreement, or the Jeffrey-Lindley paradox, shows that an alpha significant result can actually correspond to giving a high posterior, as high as 1 minus alpha, to the null. And so that seems conflicting. So all of these criticisms turn on this well-known result. To the Bayesian, that shows p-values exaggerate evidence against the null, but significance testers balk at the idea of taking highly significant results as evidence of no discrepancy from the null, or even evidence for it. In short, there'd be a high type 2 error. So the two talk past each other. Casella and Rogerberger, different from Jim, say, in fact, it's not the case that p-values are too small, but rather the Bayes point null posterior probabilities are too big. Concentrating that point mass on the null hypothesis, they say, is biasing the prior in favor of the null as much as possible. So whether or not testers should lower the type 1 error, as we hear about, is a separate question. The only problem is supposing that there should be agreement between quantities measuring completely different things and take that as the basis for why they should lower them. Why use a method that presupposes the underlying statistical model? Au contraire, the one thing that people turn to significance tests for is testing assumptions or diagnostic tests. Bayesians tend to become eclectic, like George Box does, when it comes to these diagnostic tests, which he says require frequentist theory of significance tests because we cannot lay out all of the models in advance, which would be required to do a Bayesian analysis. Once you have the models, he will go on and do Bayesian, but not at the point of testing assumptions. Another example is Andrew Gelman's falsification is Bayesian, where he says what we advocate is what Cox and Hinckley call pure significance testing. So the whole count will then move to what he calls an error statistical approach to testing assumptions. Looking just at the comparative measures, be they Bayes factors or likelihood ratios, you don't have a falsification, it's just a comparative account. Why use a method that doesn't report effect sizes? Well, it's true, the p-value doesn't, but who says just report p-values and then stop? Given evidence of real effect, we go on and estimate its magnitude. You could use confidence intervals, but these, of course, are dual to tests, so it doesn't make sense to say, ban the test and use confidence intervals. In short, all of the parameter values within the 1 minus C interval are going to be those that are not rejectable at the C or the alpha level. Moreover, confidence intervals, at least as they're standardly used, inherit the problems of Neyman-Pearson tests, that they're justified solely in terms of long-run performance, which is necessary but not sufficient for good tests, and the tendency to just use a single confidence level. I think if we take the skeptical responder a bit further, we are led to a completely different or somewhat different use of error probabilities, namely to quantify how well or poorly tested claims are. In this account, which is the one I favor, tests are reformulated in terms of a discrepancy gamma. You can avoid magnitude errors if you find out that the probability you would have gotten an even larger difference where the magnitude that high is high. And in general, that's something that's developed elsewhere. Just to give then a concluding comment, it's interesting that people take the replication crisis as grounds to disbelieve or question the use of significance tests, and yet they don't question the use of these tests in determining that there's been lack of replication, and that's what they're all based on. The enlightened significance tester would rather abolish the abuses and misuses of tests than abolish the tests themselves, but they should be prepared to respond to challenges. I think there's a constructive upshot from the replication crisis. It actually teaches us to be clearer than testers have been in the past about the interpretation and rationale of significance tests, that biasing selection effects influence error probabilities, and the error probabilities influence well-testedness. So if you're in a context where you're worried about selective reporting, multiple testing, and cherry picking, then you actually want a method that is influenced, that is directly influenced by them, and that can take account of them. Why? Because the very same p-hacked hypothesis can occur in any of these other accounts. They can occur in Bayes factors, likelihood ratios, and so on, with one important difference. Your grounds for holding them accountable for violating error control is lost, unless they're supplemented in ways that's not now common. I'm prepared to say that the goal of well-tested hypothesis is sufficiently different from the goal of highly probable ones and all the many different ways that can be interpreted, that you can use different tools for different contexts. So these were our 6 questions, and I discuss these much more in a book that is finally out. Thank you very much.